When talking about steam sterilization devices, one question emerges. What is it that contributes to the control, precision, and validation of steam sterilization processes in autoclave systems? The simple answer is F sub 0. In this video, we will delve deeper into F sub 0, what it is, how it's calculated, and how it's used. Let's begin.
We start off by establishing a relationship between the number of microorganisms and the time of sterilization, where n is the number of microorganisms and k is a constant dependent on the species of microorganisms and determines the rate of death. This equation shows that as time progresses, n changes by a factor of negative k. By rearranging the equation and taking the integral of both sides, it results in a logarithmic relation between n and time, where the previous capital K changes to small k because of changing the base of the logarithm from base e to base 10. We do this for the sake of practicality. To find the value of the constant, we take this equation at the starting point of sterilization, where time equals 0, and n0 represents an initial number of microorganisms. K gets multiplied by 0 and cancelled out, resulting in a constant equal to the log of n0. We replace the constant with log of n0. By rearranging both n's to one side and cancelling out the logarithm, we get this equation, which can be shown graphically. This shows that the time required to reduce the number of microorganisms, n, during sterilization is dependent on the initial concentration, n0, and the species of said microorganisms, in which the dependency is represented by k.
By taking time as a reciprocal of k, we achieve a relation where the change in the number of microorganisms is equal to one logarithmic unit of its initial value. The time required for this change to occur is known as d-value. This graph displays different d-values and how they affect the time of sterilization. When the number of microorganisms is above 10 to the power of 0, it represents the fraction of microorganisms remaining. But when the number of microorganisms reaches below 10 to the power of 0, it represents the probability of contamination in the sterilized unit. So, 1 over 10 should be understood as the probability that 1 over 10 of the unit is contaminated. In the equations before, the relations were established under the assumption that the temperature is kept constant. But as the temperature changes, the d-value fluctuates with it. The relationship between them is shown in this graph. This relationship is called the z-value, which more specifically refers to the temperature change needed to cause a 1 logarithmic value change in the d-value. Just like the d-value, the z-value can fluctuate depending on the type of microorganisms being dealt with. Because d-value changes as temperature changes, it can be taken as a function of temperature. And as the temperature changes by a value of z, the d-value changes by a factor of 10. Basically, the definition of z-value. With Fy being the Laplace transform of dt, using the Laplace timeshift property, we achieve the following. And when substituting them in the z-value equation, then by cancelling the Fy's and rearranging the equation, we can find y. Using these two assumptions, the Laplace of dt can be found, from which we take the inverse Laplace transform to find dt. And here, ln cancels with e. After which, by taking d and t at an initial point, the value of the constant can be calculated as d0.
Through this equation, we can establish an equivalence between the time it takes to reduce a microbial population at different temperatures. By recalling equation 1 and the definition of d-value, we substitute them in and cancel out the constants. And by recalling equation 2, we substitute it in d, where d0 is cancelled because it is a constant. The integral is solved on the left side, while the right side is rearranged. Now by taking t0 as 121 degrees Celsius and z-value as 10 degrees Celsius, and by changing the integral for summation, which also entails the inclusion of delta t, this expression of time is named f sub 0. F sub 0 refers to the equivalent amount of exposure time in minutes at 121 degrees Celsius of the actual exposure time at a variable temperature, which has been delivered to a product by the sterilization process. But how is F sub 0 used? As seen in this graph, the autoclave takes an average temperature for each minute after reaching 100 degrees Celsius during heating phase, and it uses this temperature to calculate in partial F sub 0 for each minute. This partial F sub 0 counts towards the sterilization time, after which sterilization ends when a target F sub 0, or rather, equivalent time of sterilization at 121 degrees Celsius is reached. This is how F sub 0 is utilized in modern autoclaves to achieve a more efficient sterilization cycle, aiding in saving energy and time.